Okay, it is 11, so let's go ahead and start. The first thing that I want to talk about is I have changed my office hours slightly. Instead of being Monday, Wednesday from 12:30 to 5 and Friday from 12:30 to 2, it's now going to be Monday, Wednesday, Friday, 1:30 to 5. The reason I have done that is so I will have time to drive home after this class and use my not crappy computer to try to render and upload the class videos. So it will save me a bunch of time and effort by going home to doing it as opposed to doing it on my terrible office computer here. So I'll be able to get them up in a much more quick turnaround. All right. So when we left off on Friday, I was poorly trying to draw an amplifier circuit in LT Spice. I have brought my mouse today so we can make one that will be less painful. So let me open up a new schematic. Oh, sorry, one other thing before we address this. Thank you. Just set it down over there. Your homework 2 assignment didn't get uploaded until yesterday because I forgot about it. So it's due next Sunday. So you still have a week of lead time to do it. And homework 3, which is going to be on this material, I'm not going to upload until tomorrow so that you don't have homework to do on back-to-back days to give you guys a little bit of time. So I'll probably wind up catching things back up over the break or something like that. So I am intentionally not giving you a homework today and posting it tomorrow so that you don't have them due one day after another. All right, so back to LT Spice and our op-amp circuit. If I type in UNI, it gives me the universal op-amp. Right now, I'm just going to right-click it and make sure that it is set to Spice level 2, which it is. I take that back. I'm going to set it to Spice level 4 or 3B, I guess. And I am going to throw some voltages in. And what I'm doing might seem weird, so I'll explain it. I'm going to tie these 2 voltage sources together. Doesn't matter. So I've got 4 voltage sources. Okay. And I'm just going to move this guy over here so it's not in the way. So this is the one that's probably going to make the least amount of sense to you all and the most amount of sense to me. So what I've done is I've tied the negative polarity terminal of voltage V1 to the positive polarity terminal of the voltage source V2, and I'm going to set this as my ground. Okay. Then I am going to use this guy that lets me label networks, and I'm going to call this guy VCC plus, put it up here. And I'm also going to put that same label at the positive power supply terminal of the op-amp. And so what that's going to let me do is have a much cleaner op-amp circuit because it's just going to reference that voltage. So I'm not going to have tons of voltage sources connected all in different which ways. I'm just going to call on those other voltage sources. I'm going to do VCC minus, put it down here, and also connect that to the negative power supply terminal. Let's see, ground this guy, ground this guy. And I think the example problem we were working, let's see, let's call this VPOS. And V should be minus. So this is going to be the voltage that I'm going to apply at the positive polarity terminal and then the negative polarity input terminal. Actually, let me give myself some wires. And lastly, V out. All right, and now I need to come over here and give these guys value. So what power supply voltages was I using last time? Like plus or minus 10 volts, something like that? All right, so I can do 10, and I can do positive 10 here. The reason I can do positive 10 is because the positive polarity is connected to ground. So that's the same thing as giving me negative 10 volts at VCC minus. Then I had, I think 3 volts and 2 volts. All right, and so I'm gonna run a transient simulation for, let's say, 1 second. And this is probably gonna give me, well, it should give me just a graph where when I click on V out, it's just giving me positive 10 volts. Very uninteresting. We can see that it's saturating at the positive power supply voltage, but that's boring and it's not really illustrating what I want. So what I'm going to do here is I'm going to change V positive from a simple DC circuit or DC signal to an AC signal. I'm going to have, let's see, I'm going to do 2.5 volts offset and 2.5 volts amplitude. So I'm letting this thing, it's effectively going to swing from 0 to positive 5 and cycle back and forth. And because I'm looking at it over 1 second, I want 5 cycles or so. So let me do 5 hertz and everything else should be fine. Let's rerun this. And now we can see that it's swinging from the negative supply voltage to the positive supply voltage. Let's plot it with the input signal at this. So whenever our voltage is above what we call our reference voltage of 2 volts that's applied at Vmin, we see that our output signal, which is in green, goes high. And whenever our input voltage is below our reference voltage of 2 volts, we see that our output goes low. And it repeats that over and over and over again, okay? This is what we would call a non-inverting comparator circuit. And we'll talk about that momentarily when we get into open loop circuits. But what I want to do is I want to look at this guy right around where it's changing from high to low. So I'm going to change my time axes here. So let's look at it. What I'm doing is I'm right clicking on the horizontal axis and I can change a couple of things here. So as my, let's put this at 0.1, and I might have to zoom in again momentarily. And let's put this at 0.12 seconds and 100 microseconds. Let's see how this looks. So the blue curve again is my input signal and the green curve is my output signal. And it might be hard to see, but there is a slope here. So I'm going to zoom in again. So looks like I want to look at it at 106 microseconds and then roughly 107 microseconds. Wait, let me see. 106 milliseconds maybe then to 107. All right. So we can now see that there is a definitive slope here, okay? Why that's important is that this range is actually where the amplifier is behaving linearly. Everywhere else, it was behaving non-linearly, being in positive saturation or negative saturation. So this small part of its cycle is where our system is actually acting as an amplifier circuit. So I want to figure out how we can mathematically determine that, and it's actually pretty trivial. No. All right, so let's talk about linear range. So the linear range is the values of the input signal that can be amplified without causing saturation distortion. And this is simply going to be oh gosh, why can't I? Oh yeah. Negative VCC or VCC minus, that would be a better way to do it, VCC minus, divided by the open loop gain is less than our input voltage is less than VCC plus over our open loop gain. So it should make sense that the range of input signals that we can actually amplify depends on our power supply voltages, because that's what's limiting what our maximum output signal is, as well as the voltage gain. So if we divide our output voltages, which are VCC minus and VCC plus, by the voltage gain, we get the range of input signals that we can actually amplify and force our device to behave correctly. So on your homework problem, I ask you something like, what's the linear range for these particular amplifier circuit, or the amplifier that I've described? This is how you'd go about doing that. And then saturation is everything outside of this. So it should be fairly trivial. All right, so now let's talk about open loop circuits. Or specifically open loop op-amp circuits. So by definition, an open loop op-amp circuit does not have a feedback loop. So generically speaking, any circuit that looks like this, where I'm just going to call this guy V1 and this guy V2, is an open loop circuit, right? This is vastly different than the negative feedback circuits we looked at in circuits 1, because all of those circuits had a resistor between our output and the inverting input terminal. Open loop circuits do not have that feedback resistor. So it doesn't have negative feedback, and it also doesn't have positive feedback, which is why it's called an open loop. Open loop circuits are very limited in their applications, and the reason for that is because they have a very, very small linear range, right? If we don't employ some form of feedback to bring that gain down to a usable level, all we can really do is hit our positive saturation supply voltage or our negative saturation supply voltage. But that can actually be useful. And what it's most prevalently used for is what is called a comparator circuit, where you are comparing an input signal to some reference voltage. So the first comparator circuit that we are going to look at is the non-inverting comparator. The non-inverting comparator is our basic open loop circuit. VCC plus, VCC minus, V out. On the non-inverting input terminal, we will apply our input voltage. And on the inverting input terminal, we apply our reference voltage. So let me swing back to this guy. The values from 0 to 1 with 100 millisecond increments. So in this circuit, the voltage connected to our positive polarity terminal, our input voltage, is our sinusoidal signal with that 2.5 volt DC offset. And our reference voltage, which is kind of hard to see because they're overlapped on top of each other. But that second 2 right there, or sorry, the first 2 is corresponding to the 2 volts of our reference. And so we can see, again, this is nothing more than what I described earlier. Everywhere our input signal, which is in blue, is above our reference voltage of 2 volts, our output goes positive. Everywhere our input signal is less than 2 volts, our output hits negative saturation. So there are some very, very small windows of linear operation, but we're talking, so for a voltage gain of 100,000 volts and positive 10 and negative 10 volts, what's the level of signals that we're actually amplifying? So 10 volts divided by 100,000 means any signal greater than 100 microvolts, we hit saturation. So if we're comparing something to a 2 volt signal, it's going to look like it's just swinging with completely vertical transitions. Okay. So I can say then that my input output relationship for this guy is VCC plus whenever VN is greater than V reference, and it's VCC minus whenever VN is less than V reference. Technically 0 whenever VN is exactly equal to V reference, but it's going to be really hard to ever see that because the linear range is so small. So this is how a non-inverting comparator works. Pretty simple. Then we have an inverting comparator. almost an identical circuit. But instead, we apply our reference voltage to our non-inverting input terminal and our input voltage to our inverting input terminal. What we should expect to happen is that we get VCC minus whenever Vn is greater than Vref, and we should get VCC plus whenever Vn is less than Vref, and we can verify that very easily using a simulation. So if I changed I put that input signal on the negative, or that sinusoidal signal on the negative, and I put the 2-volt DC term on the non-inverting terminal, and I run my simulation. Now I get the exact opposite response, right? So whenever my input signal is greater than 2, my output goes low. Whenever my input signal is less than 2, my output swings high. Very, very basic circuit. It is really the crux of inverters. Everything beyond this is literally just thinking about how we're going to generate our reference voltage. And what I mean by that is, so let's say that I wanted to make a very, very simple analog to digital converter, okay? So this is a very simplistic design problem. You want to make simple analog to digital converter where any input voltage greater than 3 volts gives you a digital high, five volts at the output, and any input voltage less than 3 volts gives you a digital low of 0 volts. How might we go about designing something like this? That was the bottom of the page, but I think we can actually fit that design in that little bitty amount of space. This is pretty simple. If I can stop my fat fingers from going over and making it advance. Okay. Any thoughts? Okay, so we know that our reference voltage should be 3 volts, okay? I 100% agree. So VCC plus should be 5 volts because we want our maximum positive output to be 5 volts. But I would disagree that VCC minus should be negative 5 volts. Because it should be 0 because we want our output to swing to 0 whenever this thing goes low. All right, so we know what VREF is, we know what VCC plus is, we know what VCC minus is. So all we're doing in this analog to digital converter is simply comparing our input signal to that reference signal. So we're obviously going to be using a comparator, but should we be using an inverting comparator or a non-inverting comparator? A non-inverting, right? Because when the voltage is greater than our reference, we want it to go high, and when a voltage is less than our reference, we want it to go low. So in its most basic form, Vn, Vref, VCC plus, VCC minus, yeah. Now, my question to you guys is, what if we didn't have access to a 3-volt supply to give us our reference? How could we go about using some other sort of network to give us a 3-volt reference? Yeah, so a simple voltage divider on the input of this guy, right? So I'm going to go down to this. So I would argue actually, I'm going to do it that way. Bless you. So there's ground rail, there's a positive 5-volt rail. We have a simple voltage divider circuit there. And here's where we're going to apply our input voltage Vn. So that begs the question then, what size resistors should I use in my voltage divider circuit to bias this thing correctly to give me this pin? Yes, sir. Okay, you're 100% correct. So the resistor on the bottom needs to be 1.5 times larger than the resistor on top, because our output voltage, our reference voltage is 60% of that 5 volts that our supply is giving us. So I could argue that we could do this a very trivial way. 3 kilo ohm resistor there and a 2 kilo ohm resistor there, and that solves it, right? So I want to see, we're going to simulate this in a moment, but I want to see if the practical op-amp model holds up to this circuit. So let's draw that. All right. So there's no feedback. And additionally, we're not driving a load resistance with this guy as it's drawn. Let's use the values that we've used in all of our other examples. AV is 100,000. RN is actually, so let's say AV is 100,000, RN is 1 mega ohm, and R out, because I can't remember what I used the other day, so I get to make up new numbers today. AV times VD, R out, RN. So here's our practical op amp model. This is our output voltage V out. So our positive polarity input terminal is tied to our voltage V in, which I'm just going to represent over here by a DC voltage source with a value of V in. Then we have from the inverting input terminal to ground, we have a 3 kilo ohm resistor. And from our 5 volt supply, so I'm trying to figure out how to quick because I kind of backed myself into a corner. There's our 2 kilo ohm resistor. All right. So that seems reasonable. Okay, does anybody see any issues with the way that I've drawn this? Let's start there. So, oh, I didn't ever draw my output voltage, so I suppose I should do that. So plus, minus, the out goes right there, so that's why it's from the output terminal to ground. My 3K resistor is between the negative terminal, so let's label that. V minus here, V plus here, which means this is my differential voltage, VD. My 2 kilo ohm resistor is between my 5 volts supply voltage and the inverting input terminal, so that's where that is. And I've also had to include my 5 volt supply voltage because the supply voltages aren't part of the practical model there. And then my input voltage is applied between ground and the non-inverting input. So everything seems okay. So it should be pretty easy to see that V out is going to be my voltage gain, 100,000 volts per volt, times my differential voltage VD, which is V plus minus V minus, whatever that happens to be, right? If I had put a loading resistor here, I could do voltage division and figure out what it's going to be, but because I have an open circuit at my output, this is how it's going to behave. So we need to then determine what VD is, right? Because we're going to need to know that. So let's see here. If I apply Kirchhoff's current law at the inverting input terminal, I'm going to have that current, and that current. So I would have V minus, minus 5 volts over 2 kiloohms plus V minus over 3 kiloohms plus V minus Vn over Rn is 1 mega ohm is equal to 0. So what I'm trying to figure out here is, does the op amp, the presence of the op amp, screw up my voltage divider circuit, right? Because the op amp has some resistance and all of that kind of good stuff too. The in is V positive. I think about how I want to approach this. If I want to just set Vn to some value, which is probably what I'm going to have to do here. So let's just, for the sake of argument, that Vn is, we're testing something to see if this is going to behave how we expect it to behave, okay? So with Vn at 4 volts, this is effectively a one equation, one unknown thing. So with Vn is 4 volts, does the voltage V minus, is it approximately our expected reference voltage of 3 volts? Meaning, is this resistor biasing network operating how we expect it to? Well, let's find out. So I'm going to use my calculator, simple numerical solver here. V minus is what I'm trying to figure out. So I'm going to have 5 over 2,000 plus x over 3,000 plus x minus x minus 4 over 1,000,000, so 1 times 10 to the 6th is equal to 0. And let's solve for x. And I get V minus, which is equal to Vref, is equal to 3.00120 volts. So it's not exactly the 3 volts that we expect it to be, but it's pretty dang close. So can any of you tell me why I can use a simple voltage divider circuit to bias this thing, even though my transistor, or excuse me, not my transistor, my op amp has internal resistances which should affect things? Yes, sir. Exactly right. The input, as long as the input resistance of your op amp is significantly larger, and so in this case, a mega ohm is almost 1,000 times, or so it would be 500 times larger than this guy and 333.33 times larger than this guy. So our input resistance of our op amp is so large that effectively very little of the current is going to branch off and flow through this input resistance. So the voltage divider works pretty much exactly as we would expect. If we screwed around with things, so we used a 2 kilo ohm resistor and a 3 kilo ohm resistor here because they gave us the right ratio. But what if we used a 2 mega ohm and a 3 mega ohm? Would that mess things up? Absolutely, right? So we have to be very, very careful about the types and the sizes of the resistors that we apply. You guys probably didn't even notice this, but in all of the Circuits 1 op amp problems that I created, and I believe that Dr. Hummel created as well, we always put in the kilo ohm range in all of the op amp circuits. We never used ohm resistors or mega ohm resistors or anything like that. And it's for this reason. We actually want to make sure that we use everything in the kilo ohm range because that's significantly larger than what we should see for any reasonable resistance. And it's significantly smaller than what we should see for any practical input resistance. So that's the sweet spot. The kilo ohm range of resistors is really the sweet spot for biasing general purpose operational amplifiers. Okay. Yes, sir.
Just trying to make sure I understand. So you're saying that we want the range to be significantly higher than 50 ohms and significantly lower than 1 megaohm.
Right. We want our resistors larger than this guy because, okay, so if I put a load resistor here, that would affect my output voltage, right? If my load resistor is of the same scale as my output resistance, I would see half of the voltage drop over this guy and the other half of it over. Whereas if this resistance is appreciably larger, almost all of the voltage drop occurs over it because of Ohm's law, right? So that's why we want our load resistor here to be larger than R out. And we want our biasing resistors over here significantly smaller than R in, so that we'll know that none of the current will flow into the op amp and everything else will behave how it's supposed to be. Does that make sense? All right. Well, we finished half an hour early today because you guys are smart and you actually answered my questions well. Oh no. So let's take them and throw this new circuit into LT Spice and make sure that our simulation works, and then we'll call it a day. We'll get into positive feedback circuits on Wednesday. So let me kill this. Let's see, kill that, kill that. Drop a ground right here. I'm going to put a VCC plus right here and on the other one. That's all right. Yeah. Simulate it. Oh, I need to label these resistors. So this guy was 2. This guy was 3. So here is our output voltage. And it's always 10 volts. Why is that? Why is my output always VCC minus? So let's think about this. All right, so I am comparing this to, let's look at this voltage right here at this node. Oh, because my supply voltages aren't correct. So when I moused over this guy, it told me that this voltage is 6 volts, which doesn't make a lick of sense. Perfect sense when my supply voltages are plus and minus 10. So let's fix this guy to 5. Fix this guy to 0. Rerun it. There we go. Yeah. All right. Now everything's hunky-dory. So we can see whenever our input voltage goes greater than 3, we swing high. And whenever it goes less than 3, we swing low. So everything's behaving like it's supposed to be. Now, before I let you guys out of here, this is a very, very simple question. But what would happen if we had a noisy input signal? Meaning that if around here it oscillated, right? So let me see if I can remember how to do this real quick. So we don't need our reference signal anymore. I want a behavior voltage source. This might take me just a second to do. It's been months since I did this. That's not giving me noise. Let me Google it. Okay, 286 times time. That's too much. It's going to take forever. All right, so now we got a real noisy looking input signal, okay? What do you think is going to happen when to our output signal when we're close to the reference voltage? Yeah, it's going to swing. So if we zoom in here and we just look at it from 0 to 1 second, or 0 to 0.1 seconds. We can see, maybe a little hard to see, but whenever we're around, whenever we have noise around our reference voltage, it swings wildly back and forth, polarity, positive supply voltage and the negative supply voltage. So what we're going to talk about in the next class meeting is positive feedback circuits, where we're going to introduce effectively a little bit of memory into our inverter circuits in order to make them latch to a particular value. So that if there's small variations, it'll still stay high. You know, if it's small variations above what we call the upper trigger limit, it'll stay high. And if it's small variations around the lower trigger limit, it'll stay low. So for instance, just as a quick example, when you guys were in engineering, I guess it was 120, so roughly 2 years ago or so. But it's been a hot minute for those of you that weren't transfer students. The Arduinos that you guys used, there was something, when you used the digital pins or whatever, when it was above, I think 3 volts, it considered it to be a positive 5 volt it gave you a 5-volt output. And when it was below, say 2 volts or so, it considered it to be digital low or 0 volts. But if it was between 2 or 3, you really didn't know how the Arduino was going to process it. This is a circuit that fixes that kind of thing. It forces it to say, as long as it's above 3 and until it gets below this certain threshold, it latches at the positive supply voltages. And until it's below this other thing and goes all the way up to beyond the other threshold, it latches low. So that's what we're going to talk about on Wednesday. And if we have time, we'll also talk about using positive feedback to create an oscillator circuit. So completely DC circuit with an op amp, but positive feedback makes it ring as if it were a sinusoidal source. So, all right, that's enough out of me. If you sign the roll sheet, great. I'll see you later. If not, come up here and sign it, and then I will see you later after that. Have a good rest of your day.